Hello and welcome. All right, let's do this. We are starting another session of hacking on the Raspberry Pi Pico emulator. And first of all, as usual, let me know in the chat that you can hear me and see me and all is okay and I'm not talking to myself. And meanwhile, let me get started by sharing my screen. So I have no idea what we were doing last week. And before we get back to that, like I got all these GDB stuff open, and I think I'm starting to remember we were looking at this SVC instruction. But before we dive into the details, let me show you something that something nice that happened this week. So it was somewhere. We have too many tabs. Let's close those. Those are from last week. Yeah. This MULS instruction is starring in the issue and in the issues. And this week, a guy named Kilogram, which is Graham Sanderson, that's his name. Kilogram is his GitHub username. He sent me this. He opened this issue about a possible error in MULS implementation. And it says that multiplying two numbers just like that may give us the wrong result because since this is like JavaScript treats all the numbers as doubles, multiplying two numbers will give us a result in like the multiplication will be done with double precision floating point numbers. And this actually doesn't give us enough precision to hold the result of two 30-bit number multiplications. So we might get a result a bit off. So it sounded right, but I wasn't sure. I mean, I would at least like to see an example of this. So I went ahead and Googled that and found this Stack Overflow where it says that multiplying those two numbers in JavaScript and taking the lowest 32 bits. Let's actually open the Chrome console and show that. So that should be the result. The low 32 bits of this should be 1, but if we do it and then we convert it to an unsigned integer or even a sign, it doesn't really matter, we can see that the result is 0. And by the way, hi Steve, hi Tomasz, and hi Valerio. Great to see you all coming back every week. It really makes me happy, so thank you. He suggested to use math.imul. So I opened the docs and I see that it returns the result of the still like 32 bits multiplication. And that's what we want to do, to multiply 32 bits number like we would do with C and get like the lowest 32 bits. And they also have a bunch of examples there, and I'm not sure if those examples would fail the standard like if we just multiply them normally, we'd get a different result. Let's try that. I think those are like pretty vanilla examples. Yes, you see you get, you don't get, that returns 5 and the result should have been -5. Anyway, so no, multiplied. So those examples aren't good examples of how this is different from what we did. But this one, if we try this one, if we pass these numbers to imul, you can see that the result is indeed 1. So yeah, there is like an edge case. Multiplying those two numbers on the real Raspberry Pi is supposed to return 1, but currently we are returning 0, and that's a bug. My bet is that if Graham wouldn't pointed out this bug, then we would probably never figure out it even exists. It sounds to me something that is pretty unlikely to happen in a way that would affect a program, but if it did, it would be a real nightmare to spot this bug. And I also looked at his profile, and it seemed like you see he started contributing really a lot of stuff since January 19, and I think it was around the time the Raspberry Pi Pico was released. I think it was the 20, no, that doesn't make sense. Raspberry Pi Pico. So I think this is a nice correlation, and it doesn't say probably in Wikipedia, but yeah, Wikipedia, Raspberry Pi Pico, yeah, okay. So never mind, I think it was around that time, and if you check out his contributions, they are all like to the Pico SDK, to the Pico examples, and all those repos that we work with. And I was actually a bit curious because his name seemed familiar, so I started looking at his contributions, and I found that where I recognized his name from, he's the committer for the boot ROM. Like all the 2 commits are under his name, so it's probably pretty familiar with the RP2040 if he has written parts of the SDK and the boot ROM, and that makes me happy that he's helping us out with this and finding those subtle bugs. So thank you, Graham. Please keep doing this, and if there is anything I can do to help you in any way, then let me know. I would love to, and thanks for that. So anyway, let's start by fixing this small, but I don't know if it's significant, but it's obviously a bug, so let's fix it. As usual, we'll write a test case, and let's do that. And Wikipedia hit it pretty deep in the article, said Tomasz, and it was released in January 2021. Yeah, the only thing I wanted to find out is when. I think it was January 21, but I'm not sure. Anyway, tests, yeah, RP2040 spec and RP2040, and then, oh wait. We have some console log here, commented out from last time. Let's remove it. I don't want console logs in my Git code. Okay, and then we have this test for MULS, and then yeah, we have a bunch of them. So let's it should execute a MULS. Wow, what happened to the test? Maybe. Okay, should MULS to large MULS instruction with large 20-bit numbers and produce the correct result. Okay, so now we'll just write the failing test case. So multiply this by this, we expect it to equal 1. Cool. Don't need to assert about the flags, and for some reason this test stopped running. This should be ready in a moment when the tests will hopefully be back in a minute. And meanwhile, we can go to the implementation of MULS. Oh yeah. Yeah, expected one received 0, but we know the fix is super easy. Just math.imul and those 2 numbers. Cool. I think it should be green. Yes. So yeah, easy fix, hard to spot bug. And now we can commit that. Our first commit, pretty quick. RP2040 bug in MULS. instruction, and that should close issue. What was the issue number? 5. And I love GitHub because as soon as I commit this and push this, the issue should be automatically closed for us. Let's see if this happens. I mean, it should. But anyway, it's fun to see that it happens. Okay, pushed, and the issue wasn't closed. Maybe we need to refresh. Yeah, it's closed. So yeah, we fixed that in this commit. Nice. No longer a bug, and we have a regression test. All right, let's get back to where were we last week. Let's look at the Git log to see if we have any things. No, we didn't leave anything in the Git log. Oh, yeah, we have this missing instruction, SVC. So let's see what is this SVC all about. SVC, let's see. I think it's system call or something like that. Supervisor call. All right. So this is the encoding. It gets a number and it 0 extends it, and then call supervisor. What does call supervisor do? All right. Yeah. Caused an SV call exception. So I guess it just raises this exception. Exception number 11, SV call. And then how do we... Okay, let's start with the encoding and decoding for it. So usual assembler spec assembler.ts, and I think we have, yeah, we should have the test case from this file. So this is encoded to that svc0, and yeah, str yeah, so it should correctly encode an svc0, not the hub, svc0 instruction, and we expect opcode svc with 0 to equal probably this. Never remember if I have to flip. I think we have to flip the byte order if it's coming from GDB. All right, and then we can probably remove this. And now let's implement this opcode. Opcode svc with IMM8, and since it's IMM8, we can assume it's like 8 bits, right? Where was that? SVC opcode SVC. Yep. Yeah, 8 bits, and then the higher 8 bits should be just this number shifted by 8 because that's the higher 8 bit. And finally, let's import it, svc, and it's already green, so all is good. Cool. So we got encoding, and now yeah, let's write a test case for it, and then we'll implement it. So rb24 spec ts, and probably just before sxtb. Yeah, here it is. It should raise an SV call exception when svc instruction runs. All right, and then we have here opcode svc, and it doesn't really matter. I think the number is like the microcontroller isn't doing anything with the number. It's just for assembly and disassembly. And if there is like operating system or something like that, it can look into this byte in the program memory and see what the value was, but the MCU doesn't really care about this value, just ignores it. So whatever, 10. And then after executing this, we expect the exception to be raised. But what does it mean to raise an exception? How does this work? I'm not sure, because it says it calls supervisor, and yeah, there isn't a lot of information here. It just says it generates the exception, but I think this exception shouldn't always be generated. I'm not sure. I mean, there is like, we have this exception priority that we did last time. RB2040 exception priority. And I think there are like some exceptions with higher priority. Let's see. Yeah, SV call is like, there is like configurable priority. So I guess it could also have like a lower priority. So I'm not sure what we should do in this case, whether we should, let's see if Google can help with that, whether it should just ignore the SVC if there is an exception or interrupt in higher priority level, or it should SV call while other exception is running, or it should remember that it's pending. And I'm not sure if there is. Oh, this one seems good. Are they from the description? Pend SV. Okay, we don't have Pend SV. We don't care about it, I guess. We care about the SVC. In the case, all right, it may be preempted by an interrupt. So yeah, that's a good question. If anyone have a good answer for that, then let me know. Otherwise, I guess we can just it doesn't really say what happens with like let's see for a moment. If we raise this exception without on the same cycle, then it will probably return to the SVC instruction, since after returning from an exception, we restore the same PC, right? What do we do with the PC in exception Henry? Yeah, we just write the value of PC to the stack, and then I guess when we return, we read it. So we restore the PC. So I guess it would make more sense to just raise a flag that say we have a SV call pending, and then when the next instruction executes, so we'll execute two instructions, and when the next instruction executes, it will go into the exception handler. So I think we can copy some of the tests from the exception code that we did last time. We would need to set up the stack pointer. I don't know if we do. Let's do it, yeah. And then we would need to set, let's copy all of this setup and then figure out what we need and what we don't. All right, so yeah, we are setting up PC, that's fine. Yeah, so let's let's set Vitor to, I don't know, this magical address, and then this is going to be SV call. There is like a constant for that, I think. Const exe SV call. I think that was 11, right? SV call. SV call. Yeah, that was 11. So yeah, exception SV call. And that should go to SV call handler, and we'll define just an arbitrary address for this variable. So const SV call handler, let's say it's in 1, 2 here. And then here we'll just move some value into R0, and that's how we know we have like successfully executed this instruction. Cool, and we don't need to do anything else, I guess. We have this, so this is like let's try this, write uint16 at, I don't think we can do this, or maybe we can write to the flash, I don't remember. Write uint16 if peripheral uint32, and yeah, we can write to the flash. Okay, so let's do it with write uint16 at rp24, or you can say at this address we want to write this opcode svc. Right, and then cool, and now we execute 2 instructions, and SV call handler should run here. And now, all right, so we expect a few things to happen. First of all, we expect the PC to be just after SV call handler, like after the first instruction, because we expect it to have executed. Obviously, it doesn't happen yet because we haven't implemented SVC. And then we also expect R0 to have this magic value of 55, because that's the first instruction in the SV call handler. And now let's implement the instruction and see if the test passes or not. All right, so let's go to this very long function with all the instructions. SVC comes here. So if opcode decoding it, SVC, if the 8 bits are like this, then we don't really need to decode IMM8 here because we are not doing anything with that. Just say this dot pending SV call true, and this dot pending interrupts true, and then we'll have this pending SV call. Yeah, let's add this. Why isn't it happy? Ooh, pending interrupts is a number, right? So how does that work? Don't remember. Oh, interrupts updated. That was what I was looking at. SVC. All right, this dot interrupts updated. Okay, and now let's add pending SV interrupt SV call. Yeah, boolean false, and then when the interrupts updated, we are checking for interrupts, so actually also for exceptions, and all right, so in this case, yeah, we need to check also if there is like an SV call. And I think if I remember correctly, the rule says that like lower exception number wins. So we need to check before we check for the interrupts which have higher exception number. So if pending SV call, and let's do const SV call priority is, we'll figure it out in a moment, and priority equals SV call priority, then this dot exception entry exception SV call, that's 11. Oh, this is green, great. We need to return. So the test passes. This works perfect. That was quick. We just need to make sure we get the SV call priority correctly. So for that, let's have SV call priority. Let's create a getter that will. We already have like this logic here. We just need to make it reusable. Okay, get SV call priority, and then we can just say SV call priority is copied from this. Okay, cool. All right, so we implemented SVC, and now it doesn't work anymore. I guess the SV call priority is, I don't know. Let's see, -1. How comes it's -1? It shouldn't be -1 in any case. Ooh, yeah, we need an unsigned shift, probably here, or we need to just take the 2. Yeah, I think that wouldn't change anything. Yeah, either unsigned int or take the unsigned shift or take the 2 lowest bits. And now it's green again, so it's good that we have this test. We just found another small but important bug. Yeah, now it makes sense. It's uninitialized memory, so it's Fs by default for us, but that's fine. I guess we'll need to make sure that when the code runs, it's initialized correctly. All right, so I think we can commit and hope for the best. Feed Arduino implement svc sv call. How do we write this sv call? Is it like, it's not all caps, it's like that. And yeah, so maybe it would make more sense to name this getter, where was that, SV call with uppercase C. Yeah, I like that a bit better. SV call, yeah, good. Yeah, let's remove this. It's easier to see what's going on in the diff. We change this one. Oh yeah. Yeah, sometimes it just doesn't rename it correctly or the way I want it to. Anyway, now we fix that. So we implemented svc sv call. Let's see, we added the opcode and with a test case and this pending sv call. Okay, I see another bug. Good that I review. If we do this, we need to say this dot pending sv call is false. Actually, let's add this to the test case first. So make sure the test catches it. Expect Arduino 40.to equal false. So we want it to be true after the first instruction and then false after the second one. And now let's fix this bug and green again. All right, so now it won't execute it repeatedly, which would probably make our program go crazy. Okay, so one more bug fixed before it hit us. So we were looking at this. So that's one of the advantages of just looking at the code before committing. You sometimes remember things. Okay, cool. What's there? This is the SVC. All right, seems pretty good, I guess. Pending SV call, interrupts updated. Okay, this should be good. Commit and push, and one more instruction. Yay! All right, let's see what's up with our current project, which, to remind you, is not written here. Let's write it down. So run Arduino Core, which is based on Mbed OS. Blink in the emulator. Okay. And we also have like this blink hex, and yep. Let's just run it and see what happens. Probably nothing too exciting. And then we'll plug in GDB. I mean, even if it works, we can't really know what's going on here. But yeah, it gets to FFFF. That doesn't seem like it works correctly. All right, so next, let's get back to GDB. We already have it open from last week, so let's restart it. All right, and continue. And then where are we? Nowhere. But oh, this looks nice. OS RTX thread switch. So it seems like we have some layout assembly. Yeah, it seems like we had some threading mechanism and something doesn't work correctly there. So it should probably, I mean, let's put a breakpoint there, but it's nice. It seems like they have like some kind of multi-threading built into it. Okay, so break here. Oh, let's restart this. Now let's connect GDB again. T-break here. Continue. And there we go. So SVC RTX kernel start, and I guess that has been called by our SVC call. Okay, let's take a look at what's going on here. Just go over the instructions. It seems to be pretty short function. So loading 2 into R3, pushing R4 and LR, which is LR is like where we are returning. We can see it's like the function that called us. Okay. Next instruction. And then we are storing R3, R0, probably storing something. I mean, where is the source code for this? Why are we working so hard? I think that's one of the disadvantages of working with like the Arduino Core, is that debugging isn't like they compiled everything for us, but then we don't get to debug with the sources and everything. And this is probably something we can overcome, but I'm not sure I want to spend time on this. So we'll see how this goes. If this becomes too complex, then we might switch to try to compile it ourselves. But for now, let's see. Maybe we can. When that's very old. No, January 23, 8 days ago. Yeah. But where's the source code for that? Let's try to embed with Arduino Core. Let's try, yeah, that sounds pretty promising. And then probably here, embed. Yeah, if you don't know, there is a really cool project called GitHub 1S, and it just opens any arbitrary GitHub repository in Visual Studio Code in this web browser. Super useful for situations like that, where you just want to quickly search something and explore the code. So yeah, we can now find this function. But where is it defined? This is not, yeah, I know. Okay, good. There is like this function. It's inside course Arduino Mbed SimSys RDX, part of RDOS 2. Okay, it's extern, but who defines those? Is it like, where's the sources for that? Let's see if there is like rdxlib.c. Not really. This is like probably the Mbed Core RDOS, I guess. Source RDSIL. Okay, let's just try to Google this function, maybe on GitHub, and see if there is like rdx3 thread.c. Yeah, that sounds right. Okay, so yeah, I guess R3 is 2. Oh yeah, R0, it's like the parameter, it's like the thread object, and then we are just storing this this is value, this is the 2 that we are storing here into this state thread running, and then this is probably this second store is like those 2 next lines, like storing, yeah, let's put them side by side, storing this thread value into osrdxinfo.thread.run.next, right? And then so yeah, and then we are calling this osrdx thread stack check, and eventually we have this evtrtx thread switched, which, let's see if we have it here somewhere. Isn't really defined here, but maybe it's defined here. Maybe we'll open this one with GitHub 1S. All right. No, that's not what I wanted to look for. I wanted to look for this one. Yeah, weak void. Event record. What does this do? Yeah, multiple implementations, so much fun. All right. Probably just recording debugging event. So yeah, so I guess the magic happens in this RDX thread switch, and then when it's like doing this pop, it's like the stack has changed. It's returning. Let's skip that instruction for a moment. Oh, let's print the S pointer, stack pointer, and then if we skip that instruction and then print, where are we? Oh, we didn't skip. We are now in this thread stack check, right? That's, yeah. Let's finish running it. No finish. Okay. Probably something goes wrong there. Or I don't know. Yeah, let's restart this. Let's put them side by side. Okay. And yeah, restart this, the emulator and GDB, layout assembly, break. What did we call that function? That was osrdx thread switch. Continue, and it should get there in no time. Cool. And now we just, skip, go into this second function, and let's see how that goes. It doesn't seem very long. Oh, that was pretty simple one. I don't think it did a lot, but let's print the SP. Seems legit, right? Okay, so now we return here, and let's print the SP again. And yeah, it seems legit, like it hasn't been changed. Let's go. Yeah, now we return to this, and yeah, this is pretty annoying that we don't have this complete call stack. I don't know why that happens with this specific build, because it worked better on other builds. I'm wondering whether, no, let's not do it yet. There is like, let's keep going over this function, rdx kernel start, and hope we hit this undefined. Interesting. Okay, let's restart and set another breakpoint in this function. Break here, continue, layout assembly, right, and let's just go over whatever. So thread new. Don't think, yeah, finish somehow messes up things, so let's do it like before. Let's break here. Break here, continue, layout assembly, and then just go over instructions. Okay, going over the instructions. So, yeah, load, branch equal. What does this do? R3 is putting the value 2 inside R3, or inside, like, the value 2 inside control. What does control do? I remember we did something, like control did something. RB2040 control. Oh, we switched the stack. Interesting. So this is probably where shit hits the fan, when we are switching from we are putting the value 2, so switching to SP process. Interesting. Let's print the value of SP now, and then if we execute that instruction, and yep, that's the problem. I wonder, yeah, I wonder why this happens. If there is like a bug that we have somewhere, that or is it expected that the boot ROM initializes the, like, we haven't executed the boot ROM, we just skipped that part altogether. So perhaps the boot ROM is initializing this stack pointer. Let's try to take a look at this, the sources for the boot ROM. So yeah, there is like MSR is like writing, right? MSR, yeah, move register into spatial. There is like magic numbers look good, so let's jump straight into the code. Okay. Yeah, but we are interested. Oh yeah, MSP is like the main stack pointer, so we are doing some stuff here, not sure. MSR, MSP R1. Again, it's loading the main stack pointer. That's like I guess the part where it loads like the set up the vector pointer and jumps to the reset vector. I remember that. Oh, wait a second. MSR PSP R1. That's okay. That's an example here. I don't know what this says, but it seems like a bunch of chips that are not really related. Seems like everything here is under the tiny USB. So what's that? Again, that's like tiny USB. Let's try to exclude tiny USB from the search results. Tiny USB. Okay, let's yeah, that's the CRT0. So it initializes the main stack pointer. I don't see any kind of initialization for the process stack pointer. So either it's somehow magically initialized, yeah, I mean, or we are probably missing something, how this got initialized in the true pipe, in the physical Pi Pico, but not in our emulator. Okay, let's see. We have a few options. One of them to try to see what happens on the real hardware, on the actual hardware, and try to read the value of, let's see if, I guess info registers doesn't show that. I don't think, yeah, it doesn't show the 2 stack pointers, which is a bit of a shame. But we can probably force it to run MSR control R3 and have some value in R3 to switch the stack pointers and see the value of the stack pointer in various points. So that would be one way to go. Actually, let's try that. Why not? Let's target. So right now, the Pi Pico on my desk is, I think it's running the Blink program. So a moment, let's just take the opcode for that MSR. So disassemble this without a star. Focus command window. Okay, let's disassemble this. Yeah, this /r to disable. Okay, cool. That's what we want, those bytes. Let's put him aside for a moment. All right, so target remote Raspberry Pi 333. That's the open OCD I got on the Raspberry Pi that is connected to the Pi Pico. I showed that setup earlier in one of the streams. And yeah, we are somewhere interesting. Now it does have some of the I mean the L file doesn't correspond to the binary I'm running now on the, I think so. I think it doesn't correspond to the binary I'm running on the Pico. I think it's just the standard Pico Blink example, not the Arduino one. But let's just to practice see what happens where this is where we are. Oh wait, but if I wanted to, I don't think I can sprint. Interesting. Maybe I can do something like that. Wait a second. Printing SB. Okay. Let's set debugger mode 1 to see what goes on the wire. So that's the initial value of SP. And now let's try to set control to 2. So what did it do? Ooh. Is supported. Setting register 16 to 2. Does it somehow affect $control? Okay, it seems like it can read and set control. Interesting. So let's see the value of SP now. It's pretty much the same. So I'm not sure if we actually changed control, if we get the same stack pointer. Let's try it for a moment with our emulator. Print control, it should be 0. Oh, here it doesn't have a control register. Interesting. So yeah, interesting. When it's connecting to our emulator, it doesn't have this, no registers. Okay, let's restart it for a moment. Now reconnected, print control, info registers, and then target remote Raspberry Pi 333, print info registers. Oh, wait a moment. We can see a lot more registers when we are connected to the it's like the same setup, but something is different. For some reason, the actual hardware sends us a lot more registers, and we can see that PSP is pretty much uninitialized. I guess that's the boot value of PSP. And then we can see all of those. So I think the first thing we can do, and I don't know if it will fix anything, but we can just, I guess this is the initial value of the PSP, and maybe, just maybe, the Mbed OS is expecting to find that value before initializing PSP, and it doesn't, because it doesn't find this value. So let's just, initialize all the stack pointers. Where is the constructor? By default to this value. So yeah, this dot sp equals this dot banked sp, that's the second sp, which is PSP by default, equals this. Now I also want to see why we get more registers here than we have on our simulator. So set debug remote 1, and let's see. Oh, what is that? That's like the response for the G packet. And let's write it down. I think we might have packet received. Yeah, I think we may send, we may not send all the registers. So let's see if we send a packet. Let's just copy this whole thing and then compare it to what we sent from our simulator. So target remote Windows 333. Yeah, not happy. Let's just reconnect. Set debug. Oh, it's not running. That's why it wasn't happy. Let's restart it. All right, now we are connected, should be connected. Okay, target remote, set debug remote 1, single instruction, single instruction. Let's see what's going on here. Yeah, I think it's shorter. We don't send as many registers as the real thing does. No, it seems like it's the same length. So I wonder where the difference comes from, or what's the reason they have those extra registers, we don't. Let's see, there are like a bunch of reads from addresses, but those all look like flash addresses, and there is like this qxfer reads threads read packet, and it has some information about threads, but where does it Where does it get these extra registers from? What is that reading from? Interesting. It seemed to be reading from 0. What is it? 0 from memory address 0, and then it has those values, even though I don't think any of those values seem. Yeah, I guess that doesn't make a lot of sense. Yes, something is missing. I don't know why. Let's try again. Target remote Raspberry Pi 333. Yes. All right. If I type info registers, oh wait a second. It's sending this packet to fetch those registers when I type info register. So P11, 12, 13, 14, 15, 16 to read those registers. Okay, that's easy. That's the missing piece. So it has those extra commands that it sends. Okay, and then let's see what happens when I connect to info registers. Oh, I wanted to enable the set debug remote 1 info registers. No, set debug remote. Oh, I think I know. It doesn't send it because we haven't said we support it. Target remote Raspberry Pi 333. It's probably at some point says that it supports info registers. Like it says fetch register is supported, so it probably knows about it somehow. Let's see. So what do we support? It says we support XML registers equals I30. Maybe this makes it realize that we support. Oh no, wait a second. That's the request. That's a reply. So we support threads, packet supported, X for features read target. There is some, yeah, it seems like there is some XML that it sends, and that XML probably, that XML that we can't really see here, probably, let's, just try to open a connection to the OpenOCD and see what it replies. Do we have a telnet here? Yes, telnet Raspberry Pi 333. Just send this command. Doesn't like that. Yeah, it's probably expecting something else. Connection rejected. Maybe there is another way to intercept the communication, prints this XML, like this target XML, because I think that's the part that we're missing. Maybe we can try to Google this and see where it's probably a file that comes from somewhere in OpenOCD. Rich name. Yep, there seems to be. Where is that? How did they get this? Let's say OpenOCD, GitHub, or maybe OpenOCD for the RP2040. And let's see if we have any XML files here. So again, GitHub 1S, so I don't have to clone this. And then let's see if there are any XML files. That looks like target RP2040 XML, ARM XML, Cortex XML. Let's just try to search for this text. Let's for this. No luck. Okay, interesting. It comes from somewhere. Yeah, but where does it come from? GDB target. ARM6 ARM6M profile XML. Yeah, but it should come from, I guess, somewhere in the source code. Was that the OpenOCD one? Let me see if I can spot this file somewhere in my Raspberry Pi. OpenOCD, no, that's not the one that I want. Where did I build it? Maybe here? Oh yeah. Not really. I mean, the other option is that if it's not coming from the OpenOCD somehow, then it's probably, wait a second, where was that? Here. It's probably something built into the Raspberry Pi itself, but that sounds, well, you never know. Yeah. Interesting. So it finds this. Oh, is it like, yeah, I guess this XML is actually generated from this file. Let's take a look at that. So I don't have a setup with the Raspberry Pi, but we can definitely OpenOCD. Where was that? Yep. Don't have visual code that runs on top of the Raspberry Pi, but now that we know this, the file name, we can just, that was ARM7M, right? ARM7M, yep. Yeah, and then that's, I guess, that eventually generates the XML, probably. XML. Yeah, I hoped I would just find the XML, but there is probably some code that generates that, and it will probably take a long time. I just want to get the value of the XML, so I think the best way, I wish GDB would just print the whole thing. Let's try to see if I just send it. Is Q supported at the beginning if it's happy? Let's restart OpenOCD. Yep. And yeah, telnet Raspberry Pi 333. Okay, it's still not happy, even though I'm sending it exactly what GDB does. I guess it seems so. It seems like that's the first thing GDB is sending. Not sure why. Maybe if I use netcat instead, that would work better. Netcat Raspberry Pi. I think telnet is sending some other random characters. Okay, it doesn't break. I mean, it doesn't work as well. No idea. Yeah, I think we shouldn't send that plus at the end. Why do we? Yeah, just send. Oh, they send us the plus. Okay, let's try to send another command then. That was Oh, there is also a memory map. Interesting. But we wanted to read target.xml. Yeah, that was the file. Yeah, it doesn't seem to be. It sends a plus, which means something, but it doesn't send any responses when we send those comments. Just ignoring us. All right. Anyways, yeah. Let's see if, maybe we got, we can look into that later, but maybe we are just very lucky and it will just work now when we initialize the stack pointer the way it should. Wait a second, this and GDB and restarting GDB. Where's that GDB? Yep. And continue. Yeah, probably still. Wait a moment. This does look better. I mean, oh, it gets into a different address that doesn't make sense. So maybe, yeah, no, SB doesn't make sense anyway. So yeah, this didn't help. Still nobody initialized that stack pointer, that second stack pointer. Yeah, it would be helpful if info registers would return both stack pointers so we could compare with the Pi Pico. Yeah, so I'm thinking maybe we should just let's netcat listen on port 333 and see what GDB is sending and just replicate that. Yes, so GDB is sending. Oh, GDB is also sending plus at the beginning, so I guess that might be the reason Raspberry Pi wasn't happy, or maybe not. I mean, now we are sending exactly what GDB sent, but with the plus. Let's just copy the whole thing. Let's just try this. We had that command that queried for the that target.xml. No luck. Yeah, Talent probably sent some stuff that, oh, it worked. I don't know why it didn't before, but somehow it worked and we got the entire XML file. Okay, so let's try that. Let's try to respond with that. So the respond is just L and then this XML file. Let's add that to gdbserver. So let's create a target.xml. Const target XML. I have no idea what worked now, but not before. And we need an L before that. Cool. And now, when GDB queries X for features read target XML, so we need to respond with L and that. So that's in Q X first. So if CMD starts with this, then return GDB response L plus features XML, no, target XML. Okay, let's see if this makes GDB happy. Target, yeah, info registers. Target winhost 333. Did we? Oh, we need to restart this. Target remote Windows 333, yes. All right. Yeah, I don't think it even sent this query command. I can see it here in the log, info registers. Yeah, but I think we should also let GDB know that we support this. So let's do that. We should probably say here that we support X1st feature threads read, probably this one. Yeah, let's add it to our supported stuff. X1st features read plus. Yes, plus means yes, we support that, I guess. And restart this. And then target remote win host 333, yes. Yeah. Oh yeah, now it reads target.xml. Great, excellent. Let's see if we now do info registers, if it tries to, yep, it tries to read the extra registers. And we haven't implemented those Pico commands. Yes, it's not supported, so it can't read those extra registers. But now we know what we need to do next. We need to implement those registers, and we had some window with a list. No, that's not interesting anymore. Yep. So we have this list, and now we can just implement this case p read register, and then I guess the number is hexadecimal, so register, yeah, register index, params 0. Why don't we have here params? Oh, that's just CMD. Just have like P and register number, so that's just CMD substring 1 starting from the first character, and then switch register. I guess we can probably implement it differently, but for now we can just do so that's hexa, that's MSP, F12 is PSP, right? 12 is PSP, and then 13 is primask. And 14 is base pry, which I don't remember we had. And then we have fault mask, which I also don't remember we have. And then finally we have control. That's probably 16x, yeah. All right, so now we have the placeholder, and we just need to return these registers. And I guess if we are while at it, we can also like implement those lower registers as well. So if it's like 0 to, or maybe we can do if register index is between 0 and 15, just return GDB response encode hex buffer, I guess, because how do you return? We need to return uint32. Probably have something that does that already. Yeah, that. Maybe we'll have like encode hex dword or uint32 value number, and then we just return code. We can code x. Is it like when we encode them? Yeah, it's just like uint32 array. So yeah, so we can just wrap encode function. Encode, do we have a decoder for? No. Encode hex uint32 value number, just as const buff is new uint32 array with this value, and then I return encode hex buffer with this buff.buffer, but we convert it to a uint8 array, so it just encodes the individual bytes, and that should probably work. We'll know for sure in a moment. Yeah, so now we just need to encode the value of the register. So if it's one of those, it's just like CPU this dot RP2040 dot registers at register index. Otherwise, we need to return one of those. So yeah, for PSP, MSP, and Primask, I think we also have this one, which is just returning the value of XPSR. We did that before. Encode hex uint32 RP2040 dot, and this one will probably never be called because like the G command already returns this, but no, just for the sake of making it complete. And then here we just return the SP main, and here we return the SP process, and I don't think we have Primask yet. Do we? RP2040 Primask. Oh, so if PM, so that's how we read from Primask. Actually, we can just use read spatial register, probably. Read register, and is that exported? Let's export it. Then we can like, oh, interesting, we can just use this instead of like reading directly. Read spatial register, MSP, read spatial register, sysm PSP, sysm Primask, and we also had one for control. And these two ones, I have no idea what they are, so we'll leave them for now. So sysm control, and I guess we are missing some semicolons. We don't need those comments anymore because it's pretty much self-explanatory. And maybe instead of those very long lines, just return function called spatial register on index or sysm number. Just no, instead of returning this everywhere, just use this. Yeah, that's prettier. Now we just need to export those. We did to import those, and auto import doesn't work, so we'll do it the hard way. And sysm and sysm. Okay, almost there, I guess. That should be equals. Yeah, that's a utility function we have here. All right. Oh, and we need to return that. Not just get a value, but actually return that to GDB. And let's just, for those two, return 0 for now, and to do them. You know what? Let's see what they return in the real Pi Pico. That might give us some clue to what they do. So target remote winhold Raspberry Pi. Okay, info registers. Yeah, they are 0, so I don't know if they are important or not, but we have them in to do. And actually, let's also do the write part. I don't know if we will need it, but I mean, why not? All right, so let's say only we accept registers from 0 to 16 hexa, and then we can just do something like that. So switch register index, and then instead of reading will write. So this writes to xpsr, and all of those just instead of returning is just rb2040.write spatial register, and the register name and the value, and those just do nothing. And since it's just switch, we actually need to so add a break after each case, otherwise it will fall through, which is not what we want. So breaking here as well. Then we can just move this else to the default case. Okay, and now this can also write all those registers except for these two on switch. I don't really know what they do. Okay, so cool. So now gdbserver should be a bit smarter. Let's try that and see what's going on. All right, let's see if we are lucky. Info registers. Ooh. It did read most of them, but then it got stuck after primask. Reply contains invalid hex digit. It doesn't look like a valid hex digit. Let's say debug remote 1. I guess this has something to do with this uint. I have a feeling this is the culprit. Info registers. But yeah, we see it's requesting those registers and not getting any response for this 14. Oh yeah, we need to return a GDB response, not just encode hex uint 32. Yeah, not just 0. We need to return a proper GDB response in this case. Okay. So we blamed the wrong function. Okay, info registers. Does it work now? Yes. Yeah, and the MSP and PSP look pretty much valid. And now, if we continue and get to the state where it goes to a random location, we expect control to be 2. Yep. And we can see that MSP is valid, PSP not so. Cool. So yeah, we added a cool new feature to gdbserver. And now we can also gdbserver support extra registers. E.g. we support here MSP, PSP, control, etc. Cool. That's pretty useful. Oh, we also need to commit the changes to this one because we exported those, otherwise the code won't be valid. So let's amend the last commit. All right, added this, and then we can push. All right, now armed with an even better GDB. Last time we made it faster thanks to by disabling Nagel's algorithm, and now we can try to figure out if we can see try to figure out why PSP is initialized like that. It shouldn't. It should be initialized somehow, but who initialized it? And by looking at let's try something like that. let's try. So we have this L file. Let me copy this. Let's try connecting to the Raspberry Pi, and I think there is a way to load this L file through GDB. I don't know if that's gonna work, but let's try. I think if we type load, it should actually load this into the flash. It seems good. And then we can target remote monitor reset health and continue, and that should hopefully, maybe, I don't know, where are we? Yeah, I think it seems good, that stack trace. So maybe that updated. I mean, on the physical board, the LED is still blinking, which is what it was doing before, but it seems like the code, the stack trace seems valid inside the idle loop, whatever. We can actually try to, oh, yeah, let's do that. Break inside loop and see, yeah, it seems, I'm looking at the board now, and yeah, it seems like the LED is going off when it hits this line. So we are debugging the right thing, and then if we do info registers, we can see that the PSP does have a value. But if we do target remote reset, no, monitor reset halt, and info registers, oh, it already shows us that the, oh, it doesn't, info registers, we can see that after reset, oh, where are we? Let's execute one instruction. Okay, now info registers, yeah, we can see that, interesting. So apparently PSP is initialized like this, but this is interesting. This is the first time that I see like the how the registers are initialized after after the boot, I guess, after the boot process, and I didn't expect that. So maybe we can, if we are already there, we can update the microcontroller to, I guess, yeah, monitor reset, info registers, probably, yeah, monitor reset help, info registers. Yeah, so PC is F0. I guess that's the very first instruction of the boot ROM, because let's try to this as, or yeah, that should be x/x F0. Yeah, that's, oh, I got it. It initializes the stack pointer. Yeah, that makes sense by looking at, and then PC goes to EF, so disassembly EF, yeah, so EF is probably EF16. So yeah, that's EE actually, and F is the thumb width. Yeah, so yeah, it just loads R0. So I guess we are actually looking at the second instruction right now, but initially all the registers are just initialized to Fs when the microcontroller boots. I didn't know that, cool. And then we have like all those values. Anyway, I guess it's not really interesting right now to initialize them, because we skipped the bootloader anyway. It just was fun for me to look into that. And now we can, so we can see that PSP at that point when we are just starting is not really initialized. Now let's set up a breakpoint in this function that starts the, let's that was don't remember the name of the function that called this function, but let's start with breaking here. At the first time we are switching a thread, and again this is running on the real Raspberry Pi now. What is breakpoint 1? Yeah, we don't need that. Let's skip that actually. So starting from the beginning, and this is the breakpoint, and if we let's see the stack trace. So yeah, we can see the stack trace here, and if we info registers, we can see that at this point PSP is not initialized yet. So even on the real hardware it's not initialized, but at some point it is, and that's something that doesn't work on. Yeah, where are we now? In RTX kernel start, and then info registers, and now it's still not initialized. All right, let's see what's going on here. Yep. So going, what is R3 branch false? So I think at this point we are switching info registers, and PSP is still not initialized. So if I print, oh, interesting. I think I just but we just store 2 into control. It should switch the stack pointer. Anyway, let's see what's happened next. Maybe it takes one more instruction for the stack pointer to switch, or I don't know what. Or maybe GDB is not always, I don't know, interesting. It seems like SP is still the same as MSP, and we haven't switched, so maybe wait a second, then it's writing another bit. Where am I anyway? Got lost, branched, I guess. Yeah, I skipped this. Yes. C handler. Yeah, interesting. So it seems like writing to control in the real microprocessor didn't really affect the stack pointer. So maybe we got something, like maybe we're missing something. We don't know. Let's see. When we are writing to control, let's see what's the value of, it's 0. It seems to have not been updated. Let's retry that. Monitor reset, and that should stop at a breakpoint. Or oh, it got me into the bootloader for some reason. Okay, here for breakpoints. Okay, fine. Info registers, and control is 0, and then let's run until, let's see if finish works here. It does work here. There is something that doesn't quite work with the GDB in the simulator, because finish there doesn't seem to work well. All right, and then this is the part where we wait a second, maybe I mixed up MSR and MRS. Because let's take a look at the source code for this, try to understand what it should do. Okay, as we see, Oh, enable RDO stick. SVC setup. No idea which one here executes MSR. Yeah, there is like I don't know where this comes from. MSR control. And regular expression. Yeah, this is like R3, so it can't be one of those. It's one of those, probably GCC, so it's set control. And who calls set control? OS start kernel. Yeah. All right. I'm not sure if this is the same place I'm looking at right now. Need context system. Anyway, it seems like set control is, where was that set control implementation? It seems like set control is indeed calling MSR. So if it's called set control, then it's probably right, like it's updating control. But the funny thing is, if I info registers, control is 0, and then if I go over that instructions and info registers, it's still 0. So it seems like it's not really updating control, which is quite strange. And I think that I recognize here this like if then else structure where sets control to 2 or 3. So it's probably, I guess there is a good chance it's like here. Maybe we should DSP and ISP should be, is there anyone else? Yeah, or maybe we are here, SVC RTX kernel start. Yeah, this is what we are running. So we got into this, and then I don't know, it should have set control, but it doesn't seem to set control. And then if I, or no, I mean control is 0. And let's see what happens if I manually set it here to 2. Interesting. It seems like I can't set it to 2. It just doesn't do anything. All right. Maybe there is something about that in MSR documentation. Table. Yep. Control. Spatial defined if thread has. All right. Software can update the SP cell speed in privilege mode. In handler mode, the processor ignores explicit write. So probably that's the thing. I'm not sure. Explicit writes to the SP cell bits. Reset clears the processor. Updates SP cell every exception entry and every exception return. Right, so I might be back, I'm not sure. Let me know in the chat if you can hear me, see me again. For some reason, my video card driver just died. No, not sure why. Maybe it's related to this Windows update that updated the driver or something like that. Not sure, but it just restarted the whole thing as I was wondering about this. Anyway, thanks Valerio. So yeah, I was looking at this thing where the processor ignores explicit writes to the SP sales bit, and I'm thinking maybe this is the issue. So let's try to in write spatial register, let's print console log write spatial register, and this dot there is like a way to know if we are in handler mode or not. Where is this handler mode? I think it's current mode, yeah. Current mode, yeah. So, or no, maybe we can just do it write spatial register. Maybe you can just do it like first of all, let's this dot so it should only work if we are what is the type of that? Execution mode. So it should only work in thread mode, because in handler mode it just ignores it. So if this dot current mode, we only respect these rights in this case. All right, and I think this also killed the terminal. So let's restart the terminal because of the video driver crash. Amazing. Anyway, start a simulation and let's set a breakpoint. Where was that? Yeah, GDB died. Amazing. Yeah, anyway, let's just press continue and see what happens. Oh, wait a second. Something happened. I mean, it crashed, which is great because, and it did some stuff, because I think this means, yeah, we got some output, which is quite interesting. I think this fixed the bug. I mean, it crashed in some place, but we didn't have that before. So yeah, reading from an invalid address, which is not aligned. We'll figure that out in a moment, but that's good news. Let's see what is like what we have in the serial output. That's cool that we have some serial output. Yeah, this is like one of those fun times when you just hit play and things work better than they used to. Let's grep link output and get all the UART sent. UART sent into no, Steve, that was on my end. Link UR.txt, and then let's see everything that, oh, not get cat. Yeah, everything that UART sent. Let's remove these and a new lies. All right, we have a bunch of issues. It seems like there is a nice stack trace here, but we got somewhere. So first of all, let's commit this. It's a very we don't need this. It's a very small but significant fix. Fix RB2040. This allow switching stack in handler mode. All right, so this one fixed. Also, let's commit this ignoring git ignore elf files. Okay, just so it won't linger here on the list of uncommitted files. Okay, so now we got somewhere, and now let's try to understand why we got some place we shouldn't have. But before we do that, I think that has an address here. Let's put a new line here. Code module or message, don't know, location or value. What is this location though? Or RDX timer, but I want PC. So SP doesn't look very valid if it's printing it correctly, but stackmem looks valid, not sure. Stack size, entry, ID. Core OS, Raspberry Pico. Okay, I'm not sure. Let's see if we can find a function that prints this and then set a breakpoint there. Maybe, or maybe we can. So we want to figure out, maybe we'll start by figuring out why it just dies. So we had npm start. Let's remove that was in execute in emulator run. Okay, let's remove this for a moment. So it will just run, start running it straight away without waiting for GDB. And then we can see it does seem to sort of blink. You know what? Let's see if I'm not positive about that. No, I guess it doesn't hit. Let's see if it does. If it hits setup of Arduino, if it gets to the user code, like setup. No, it doesn't. All right. And it dies reading from address 1. All right, it shouldn't read from address 1, so it's obviously there is something wrong here. Something goes wrong. The only question is where. Yeah, we have a lot of unimplemented stuff. What is this memory address and MRS with unimplemented? Let's see if we have any missing instructions. Is that like the whole output? Doesn't seem so. It seems like, oh, but we do have a missing instruction. Which instruction is that? This us. What is missing there? That was 7A98. 98 DMB. Right, I think we implemented DMB, haven't we? Like, we shouldn't get this. Emulate RP DMB. There is DMBSY, but this is DMB ISH. What's that? No idea. I mean, it's again that we should skip. That was, I don't think that's, I mean, maybe it's the only thing we have before this. What is write special register? Oh, we removed that when we committed, I guess, I hope. Write spatial, yeah, it's probably older output. All right, so yeah, we have this followed by this DMB and DMB. So Yeah, I think this is the same. Oh, that's not the same. So there are like two variants of DMB. What does the datasheet say? DMB. Oh, there is option. So obviously the options are reserved, but apparently they can appear in the code. They probably don't do anything, but I guess we should just make it ignore, like that's the lowest bit, right? They're like, yeah, the lowest nibble. So let's just let's just ignore this. No, I want this. I want it to, yeah, I just want to make sure that I'm comparing those bits and ignoring the options altogether. So I won't have that unknown instruction. Let's see if this, we need to connect from GDB. So let's restart GDB and connect, continue. And it still dies, but now we don't have that noise about the missing instruction. We do have a lot of other stuff. I mean, not that lots, but yeah, some undefined writes, but at least we know we are not missing any instructions. So let's commit that as well. Fix RB2040 missing instructions, or decode all variants of the DMB instruction. Cool. Fix that. One less bug to worry about. Cool. Now I'm wondering about those reads. I think this memory address looks familiar in a way. What is that? Oh, that's something from the boot ROM. Let's see what's there. E00 ED1C. What's E00 is PPB base, and then there is E1 ED1C offset SH. I think it's implemented. Wait a moment. Funny. Our code generate that error. Like it tries to call get svcall priority or something like that, and then we don't really support this memory space. Interesting. Okay, so we can fix that. And then there is like also write to this undefined memory space, which is, I don't know what is there. But yeah, I guess we should probably have something that stores this data. And then most of the other stuff is like related to UART. But yeah, I would like to understand why it writes a bunch of error message, like where this, or what is this location? I mean, this doesn't seem parameter, or what is this number, for instance? What is this error status random number? Not Windows, Mbed OS. Okay, this may be a bit useful. Always negative. I mean, we could try the link and see what happens. There is a link here. empty. Let's visit it. All right. Error decoder. Type system, module platform, error, this error message queue related. Okay. So RTOS message queue error, but what kind of error? Yeah. I want to check something. I'm suspecting that we may hear the fact that maybe perhaps our Mbed OS is actually expecting us to implement both cores. Let's go to Raspberry Pi 333 and see what's going on there. How many if it doesn't want to connect? Oh yeah. Actually, I don't know why I said oh yeah. I have no idea why my SSH section connection disconnected. OpenOCD. Let's restart OpenOCD. Now GDB should be happier. All right. We are still there in the kernel start info thread. Yeah. So the first processor is running code. The second one doesn't. And then if we continue and just pause randomly info thread, yeah, it doesn't seem like this core is running anything meaningful. So it probably doesn't have anything to do with the multi-core. Anyway, let's set up. Let's try to understand target monitor remote reset halt, and let's try to understand how this Arduino Core works and hunt where the exception happens. So we have this Arduino Core embed, and there is probably a place where it calls setup. There should be a place or too many places. Yeah, main.cpp. So let's see. Let's set a breakpoint in main and run. And it hits the breakpoint. That's on the real Pi. Now let's switch to our emulator. And let's run it as well. So GDB can connect to it. Okay, it's ready. GDB connect and info break. I think we still have that breakpoint in the main, and let's run. And no, we don't get to main. So our emulator doesn't get to main. Now let's try to figure out who calls main. Which one calls main? So user. Oh, we can try that. We can try to target remote Raspberry Pi 333. Look at the stack trace. No Raspberry Pi? Yep. Where? Oh, there is no stack trace. Sad. Yeah, so who calls main? How do we find that out? Yeah, these are just like yeah, I don't see any call to main here. It just seems like these are various examples or something like that. Well, too bad. Okay, so how do we find out who calls main, or maybe we should approach it a bit differently. Maybe instead of trying to figure out, yeah, let's try just to do what we did last time, which is just printing all the addresses of the instructions that are running. So just, you know, console log this.pc to string 16, sort of brute force to find out where things get wrong. Okay, emulator run, and yeah, link output text, and in a moment or so we should have a very detailed trace of every single instruction that executed in the emulation. Now we can go to the end, and yeah, we can try to find the first UART sent. So that's probably the method that is sending the messages, and yeah, let's disassemble what's here. For instance, this is, so this is core util critical section enter that is executed, and this is just a bit before we start getting stuff on the UART. And which function sends stuff on the UART? That's serial put C. And what calls serial put C? That's this one. That's right. Yeah, that's right, not right, right. Okay, so we have like this HAL critical section enter that calls right. And who calls that? Right? Interesting. So maybe write itself uses that function. So let's see. UART init. All right, it makes sense that UART init will write something to UART. So maybe this is not where the error is happening yet. Yeah, since I was searching for UART, we can actually see here all the places where, like, there are those brown things in the scroll bar are all the places where something was no, there is like already Mbed OS error at this point. So like plus, so it's maybe this thing. I mean, strange. It seems to execute code from the memory, and then what is this? This AS RDX thread ready put. Okay, and then it goes to execute stuff here. SVC RTX thread new. Somehow, oh, this is still not from the memory. This one is the last place before running code from the memory in memset. Okay, I guess this is not really interesting then. It's probably just initializes something. And then again. I have no idea what I'm looking for. Basically, embed get error in progress. Yeah, this sounds interesting. Who calls that? That's trap RTX error. Okay. This one. That's EVR RTX message queue error. Okay. And this is called from here. What is that? svc rdx message queue sent. So this is where something goes wrong. The only question is what goes wrong, and I have no idea. But for some reason it calls it goes to EVR RDX message queue error. So let's try to find a code for this and see what this does. So is it here? No, probably here. No. So where is the source code for that? Yeah, but where is the source code for that? Maybe GitHub will make it. No source for code for this function? Maybe somewhere? I mean, RDX message queue. That MSG not no RDX MSG. Okay. Maybe this is that function. But message queue get, but svc rdx, where does that get from? No idea. Yeah, it doesn't look very much, or maybe it does. What does this one do? It calls message queue remove, for instance, and calls message queue get. So yeah, so and here is the branch to EVR RDX message queue error. So that's where things get wrong. Calling. So yeah, yeah. Let's start by putting a breakpoint in the actual Raspberry Pi, or just setting the breakpoint, and then input target. Yeah, I have no idea. I think let's try to restart it. I think I'm debugging the Pi Pico right now. Yep. So the physical one. So now I will start, and okay, we got here. It's called from svc handler, svc rgx message queue get. Let's now see what goes on. That's on the physical Pi. So yeah, so maybe we can find this if we look for who calls message queue get. Too many of those. Yeah, maybe we found this. SVC is probably ISR. Maybe, you know, it seems like it does have this call to message queue error. Anyway, so yeah, we have a bunch of calls here, and then yeah, this branch at +22 where it would eventually call the error is skipped. So those checks are okay, and I guess this is like, I don't know if this is the correct source code, but if it does, I mean, maybe we can, no, we don't have enough debugging symbols. If it does, then yeah, this is one of those checks, checking if the message queue is not null. And I mean, yeah, I guess CMP R1 0 BNE to here. So what is R1 is probably this MSGPTR. So I guess MSGPTR or one of the other checks fails in the emulation, which is strange, but let's see. Let's try to debug it and see which check fails. So let's restart GDB and breakpoint here, continue. Oh, I haven't removed that lots of debug printing, so we sort of, let's just write it down so I won't forget. And fails in, no, it doesn't fail here, it failed in this method. Right, so now we can remove all those debug prints. This.pc, great. Okay, so we need to set a breakpoint, continue, and now let's see what's going on in the emulator. So first comparison doesn't seem to fail. Second comparison fails. What is the second comparison? It's probably yeah, reading the MQID, it doesn't equal this value. So MQID, what is the value of MQ? MQ is at R0. Or that doesn't make a lot of sense. Let's restart it and see what's the value of R0 at the beginning. And I'm still not 100% sure that I'm looking at the correct source code, but it seems more or less to match the assembly code. So yeah, now that's 4 on the emulator, but if we target remote Raspberry Pi 333, if we switch to the Raspberry Pi, we can see it's not 4, it's something that makes sense. So there is, here we found a bug, now we need to find a reason for that. And yeah, frame 1, where do we get this SVC handler? Well, what's going on here? There is like maybe there is a problem with the stack pointer. At this point, PSP actually has the value that makes sense, so it seems like it initialized it correctly. And control is F is 0, and let's target remote Raspberry Pi 333, switch to Raspberry Pi info registers. Yeah, it seems pretty similar. I mean, at least the PSP and the MSP. All right, so let's go back to remote WinHost. Right, info registers. And yeah, so frame. Yeah, that's the beginning of SVG RDX message get. Frame 1 and how comes? Oh, BLX R7 LDMIA SVC handler. So yeah, either there is a bug in LDMIA think there is a bug in LDMIA. Let's put a breakpoint here and see what's going on there. Let's restart this thing and put a breakpoint here. Continue. Didn't hit that point. Interesting. All right, let's try to target remote Raspberry Pi 333. Where? Let's try to find a source code for this SVC handler. It will make our life easier if we can find it. SVC handler. Or maybe not so. Maybe it's written in assembly anyway, but I guess even if it does, it will probably be, there are so many variations though. Maybe we'll be lucky and there will be only one. No, just extern void. No source code. Oh, there is, or no. It's just a linker example. No idea. Anyway, yeah, there are a bunch of them. So one of them is probably correct. Yeah, this is probably not the same one. I'm layout. Okay, let's try to set a breakpoint in SVC handler and debug. Oh, restart this. Now restart GDB, breakpoint here, continue, layout ASM, and now, yeah. Where am I? How did I get there? Okay. Yeah, so let's print the value of R0 here, and here it's legit, but then let's see what's in this address. So interesting, there are like few values in this address, if I got it right, and none of them seem like a valid pointer. And then LDMIA probably overrides those. Yeah, it loads 18, which doesn't make a lot of sense, I guess. But maybe it does. Maybe like it's, yeah, maybe it does for this, in this case, like in SVCREX kernel initialize. Let's see if there is, yeah, there is another call to SVC handler. This is like not the only one. So let's see if there are like, yeah, there are multiple calls, and only in this one, like the fifth one or so, it dies. Let's take a quick look at LDMIA. I'm not sure. No, I don't think there was a bug. It seemed like it does the right thing. So how many? I think we had 5 times until it died. Let's try that again. Breakpoint here. So 1, 2, 3, 4, 5 dies. Yeah. So let's just, I think there is a way to tell GDB to execute, to count, or to execute the breakpoint a few times, or continue, skip it a few times. But since it's only 5, 1, 2, 3, 4, 5, we can just do it manually, and then just like, now it didn't branch. Interesting. And R0 is this, and yeah, there is like 4, the value 4 here. It's there, but someone put that value there. and that someone probably caused us some trouble. It shouldn't before, because then probably whatever invokes the SV call put some value there. Let's try to see how this is working in Mbed OS. So SV call. What is doing the SV call or SVC instruction? IRQ handler, but SVC, but what is calling this? What executes this SVC call? Oh, I think we had it like, wait a moment. I think we can just find we have SVC in the code, and I think we had the address in this file before we deleted it here. So let's see what is there. This OS kernel initialize call this SVC, right? SVC 0. But that might not be the only SVC. Maybe, I mean, SVC handler is probably the this SVC handler. So yeah, let's see. Let's take a look at this file with all the instructions, and let's see what happens. Nothing. No, it's not useful. I hope that would tell us, or maybe. Okay, that's probably good enough to see what happens every time before this handler executes. So that would probably be where the SVC instruction, that the instruction before. Let's see what's there. Who calls SVC? Yeah, this is OS message queue get. It calls SVC 0, and I guess this is also where it has some information about the not sure. I mean, this is probably how we get to that SVC handler. But how does it? Let's look for the source code of this OS message queue get. It might give us some clues. Okay. IRQ. SVC message queue get sounds good, but there is no implementation. Oh my. Yeah, debugging with the Pi Pico was so much easier when we had like the setup with all the source code and everything. Anyway, I think it's getting pretty late and we are running out of time. So we have made a few bug fixes today. So let's just, release what we have so far. Let's, for a moment, stash all of these files. So stash everything. Yeah, stash anyway. Weep. Doesn't really matter, and then we can work on the release. Now I actually have some question for you. So the thing is, I think I mentioned it 2 sessions earlier, 2 episodes earlier. We have this course that is coming up very soon, like starting next week basically, and we'll have one more session to work on the emulator before this course. And I really want to use the emulator for this RB2040 course. You can see how it can be useful for someone who doesn't have the actual hardware. And I hoped we will today we'll manage to get to the point where we can run Arduino code. Yeah, patch version sounds good. Apparently that didn't happen. So I guess I will probably have to work to continue do some work this week to get it to the stage where it can run Blink, because next week we have like 2.5 hours, and that might be enough, that might not be enough, but then the course is the next day, and I want it to be ready and integrated into Walkme for the course. So I'm thinking what would be the best way to continue from here. Like I can probably do this offline and then explain what I did in the next session, or I can try to record the entire thing, or we can set up another live stream. I don't know, in 2 days or tomorrow. I have pretty much my calendar free this week to prepare for the course. So I would love to have your thoughts here in the chat or on the Discord channel later. How do you want me to go about it? Should I just work offline and then update what I did, how I fix this next week? Or should we schedule more streams this week and then you can maybe watch them later if you wish? Let me know and let's finish this release. So let's see, we have a lot of small fixes. Yeah, a bunch of fixes here. One feature, but I guess it's still okay to have a patch version. Yeah, published, perfect. So yeah, so we published a new version. We got better GDB. Still, I think there is like something that doesn't work right with GDB, because it seems to be more accurate with the stack traces on the actual Pi Pico. And we fixed a bunch of small issues, especially this one, which we just killed the blew up the blink in the Mbed OS core. So anyways, I'll see you again next week, and thanks for the feedback in the chat. And if anyone else has some thoughts about how you want me to go about making Blink work before next week, let me know on Discord. Thanks for the feedback, and have a great rest of the week, and see you again next Tuesday in any case. Bye bye. Have a great week.